Hey guys, here are your notes for section 6.2 on inverse functions, day 2. All right, so yesterday we learned all about inverse functions, right? So let's just review what we saw. Inverse functions, right? An inverse function is a function that undoes another function, right? It has to undo all of the operations that another function was doing, okay? So we know x goes into the original function and y comes out. So therefore, the point xy is on the original function's graph. So pretend that 6 went into the function and 10 came out, okay? So 6 went into the original function, something happened to him, and a 10 came out. Well then, when that y value, that output out of the original function goes into the inverse function, the original x that went in comes out. Therefore, yx is on the inverse function's graph. So guys, if 6 goes into the original function and 10 comes out, then when 10 goes into the inverse function, guess who has to come out? 6. Whatever happened to 10 has to get undone, and 6 has to come back out of the inverse. That's what inverse functions do. They undo what another function did, okay? So the inverse function reverses the ordered pair. This is on the graph of the original function, and this is on the graph of the inverse, okay? So their ordered pairs literally switch. His x becomes the inverse's y. The original y becomes the inverse's x's, okay? Their ordered pairs literally get reversed. Okay, so look at example 1, because this is a fairly simple question when it comes to inverses, and I would hate for you guys to get something like this wrong. It says, if the graph of f of x goes through the points -2, 5, 0, 7, and 11, -4, what points does the graph of f inverse of x go through? Well, think about it. If these are all the points that are on the graph of the original function, think about what happens to these points when they pertain to the inverse. They have to get reversed, right? These ordered pairs tell a story. When -2 went into the function, a 5 came out. When 0 went into that function, a 7 came out. When 11 went into that function, a -4 came out. So what is an inverse going to do? It's going to undo all of this. That means that when 5 goes into the inverse, who has to come out? A -2. So that means the point 5, -2 has to be on the graph of the inverse. All right? If 0 went into the original function and a 7 came out, then when 7 goes into the inverse, guess who has to come out? 0. All right, and then if 11 went into the original function and a -4 came out, well then when -4 goes into the inverse, guess who has to come out? 11. It's going to undo whatever that function did. So all you have to do is switch the x and y's, and those become the points that live on the inverse function's graph, right? Every xy that is on his graph, there's a yx that lives on his graph. Okay? All right, so just reverse the x and y, and that's how you can get the points that are on the inverse function's graph. Okay, I just wanted to go over that with you because that's a fairly simple question that you can get asked. All right, our main objective today is going to be to verify inverse functions. So basically, you're going to have to prove that two functions are inverse functions. Well, think about it. Inverse functions have to undo other functions, right? In yesterday's notes, we saw in example 1 that the function f of x equals x plus 3 has the inverse function f inverse of x equals x minus 3. This is a fairly easy inverse to see. If this function is going to add 3 to his input, then his inverse function naturally would have to subtract 3 from his input, right? That's how it's going to undo adding 3. The inverse is going to subtract 3. Not all functions, though, are easy to see if the operations are undoing each other. So if an inverse function has to undo what another function does, then one way to prove that a function will undo another function is to prove that the operations used in each function will cancel each other out. And the way we can show that the operations in one function are canceling out the operations in another function is to prove their compositions, is to prove that when you plug g of x into f, or when you plug f of x into g, all of the operations involved in these two functions cancel out, and you're just left with x, the original number you would have plugged in, your original input. So one way to verify inverse functions is to use the composition of functions to prove that f of g of x is equal to g of f of x, which both end up just equaling x, okay? So you have to prove their compositions. This was the composition of functions that we worked on last week. Okay, all right. So basically you're just gonna plug one function into the other and make sure that the operations involved cancel each other out. If they cancel each other out, then they're inverse functions. All right, let's practice a couple examples. Okay, so example 1. Verify whether each pair of functions are inverses. And again, what we wanna verify or what we wanna prove is we wanna prove that f of g of x is equal to g of f of x, which both just end up equaling x. Okay, so let's look at these two functions. You have f of x equals 3x plus 9. You're going to plug a number in, times it by 3, and then add 9. And then you have function g of x. You're going to plug a number in, times it by 1/3, and then minus 3. Are these inverse functions? Will his operations cancel out everything that he's doing, and will these operations cancel out everything that this one is doing? Well, one way to prove that their operations will cancel each other out is to prove this. Plug one function into the other and see if everything cancels out. And then plug the other function into the other one. All right, so the first thing we're going to show is let's find f of g of x. Let's plug the g of x function into the f of x function. All right, remember we did this last week. Technically, you work from the inside out. So first you plug x into g, right? So you plug x into g. But remember, x already lives inside of g. When you plug x into function g, you get this. You get 1/3 x minus 3. So really, g of x is 1/3 x minus 3. And now you want to find f of that. So basically you want to plug all of this into function f. So let's do that. So go to function f, start writing him, starts with a 3, take x out and plug all of this in for x. 1/3 x minus 3, and then don't forget about his plus 9. All right, let's clean this up. If all of this cancels out, then we're going to be looking good. All right, so let's distribute our 3. 3 times 1/3 x is 1x. 3 times negative 3 is negative 9. Bring down the plus 9, and guess what happens? Negative 9 and positive 9 cancel each other out, and you're just left with x. That's perfect. That means that when you plug this function into that function, all of the operations cancel each other out and you're just left with x, because that's what inverses need to do. They need to cancel out each other's operations. All right, but you can't just prove one. You have to prove that it works both ways. So now we have to find g of f of x and hope that we get just x. Okay, so now we're gonna plug f of x into g. All right, so start from the inside and work your way out. First, plug x into function f. Well, guess what? If I plug x into function f, it already is there. This is what you get. You get 3x plus 9. All right, so really, f of x is 3x plus 9. So I want to find g of that. So I want to plug all of this into function g. I'm plugging the whole f of x function into function g. So go to function g and start writing. Function g starts with 1/3 times, take x out, put all of this in. 3x plus 9, and then don't forget to finish him off with his minus 3. All right, let's clean this up. Distribute. 1/3 times 3x is x. 1/3 times positive 9 is positive 3. And then bring down your minus 3. And guess what happens to a plus 3 and a minus 3? They cancel each other out, and you're left with just x. That means that all of his operations canceled his operations out. And all of these operations canceled those operations out. So you have just proved that these are definitely inverse functions. Okay, perfect. So you can say, yes, they are inverses. So now you could name g of x f inverse of x, or you could name f of x g inverse of x. They are true inverse functions, okay? All right, let's look at this one. All right, let's say function f equals this. Now, technically, I don't want to get too far into it, I should have put the stipulation that if this was going to be function f, because remember I told you, not all functions have an inverse function that exists, right? So let me just say that if we're going to use f of x equals 2x squared minus 1, I have to restrict the numbers that you plug into it are numbers that are greater than or equal to 0. Don't ask why, just go with it. I promise you, nothing on your homework or quiz will involve this, but if I'm going to use this as an example, I have to put that stipulation on there. All right, so anyway, all right, so let's say f of x equals this function, and g of x equals this function. Can we say that they are inverse functions? Well, if all of his operations cancel his operations out, and all of these operations cancel those operations out, we can say that they're inverse functions. So we have to prove that this is true, that when you plug the functions into each other, they all cancel out and you're just left with x. All right, so let's find f of g of x first, right? Okay, let's plug g of x into function f. All right, so first we plug x into g. If I plug x into g, I get this. That is g of x. So really, g of x is the square root of x plus 1 divided by 2. And I'm going to plug it into function f. So go to function f and start rewriting it. It's going to be 2 times, not x, plug this in for x, it's going to look weird, x plus 1 divided by 2, close it, square it like it was in the original function, and then minus 1. All right, let's clean this up. Well, we always take care of exponents before multiplying. So what does this square do to this square root? It cancels it out. All right, and I'm going to be left with 2 times, I'm left with x plus 1 divided by 2, and then minus 1. All right, well, what happens to this 2 and that 2? They cancel, and I'm left with x plus 1 minus 1. And what does the plus 1 and the minus 1 do to each other? They cancel each other out, and I'm just left with x. So that means that all of these operations canceled out his operations. Now let's try the other way. Do his operations cancel out all of his, right? Well, let's see. What is g of f of x? Okay, first we plug x into f. Well, if I plug x into function f, I already did that. I get this. This is f of x, right? Okay, so f of x equals 2x squared minus 1. So now you have to plug that into function g. So you're plugging f of x into function g. So go to g and start rewriting. Start with the big square root, and you get not x, you're plugging this in for x. 2x squared minus 1, and then plus 1, and now divide it all by 2. Okay, so this by definition is the positive square root. So the positive square root of, well, on top, minus 1 and plus 1 cancel. I'm left with 2x squared divided by 2. Well, that's the square root of 2 divided by 2 cancels. I'm left with x squared. What is the positive square root of x squared? It's x. So we have just showed that all, sorry, I was a little off the screen. So all of these operations get canceled out by his function. So that means that since everything canceled out to x and everything canceled out to x, you can say that these are inverse functions. Okay, let's look at this one. Are these two inverse functions? Will all of these operations cancel out with his, and will all of these operations cancel out with his? Let's see. I'm going to do f of g of x first. Okay, so first we're going to plug x into function g. Well, if I plug x into function g, I get this. I already did that, right? So really, g of x is 2x plus 5. You have to plug all of that into function f. So go to function f and start rewriting. It's going to be 1/2, not times x, plug all of this in for x. So times 2x plus 5. Okay. Oh, yeah, sorry. Plugging all of this in, 2x plus 5 goes into there, and then I still have to add the 5 on the end. Okay, now let's clean it up. So 1/2 times 2x is x. 1/2 of, 1/2 times 5, that's half of 5. That's 2.5. And then still add the 5. Well, they don't cancel. I'm left with x plus 7.5. That's not canceling out. So you can say right away that these are not inverse functions. Now again, you could double check it and go back, but we didn't do anything wrong. So I'm telling you right now, these must not be inverse functions. Now you could try the other way if you're like, oh, maybe I just did something wrong and you wanted to find g of f of x, but I'm telling you, they're not gonna cancel each other out. So this is just no, not inverse functions. The operations involved will not cancel each other out, okay? All right, look at the last one. Are these inverse functions? Will his operations cancel out all of his operations? And will these operations cancel out all of those operations? Well, let's see. Let's find their composition. So let's find f of g of x first. So first we're going to plug x into g, but I already did that. I get this, right? So that's going to be f of x minus 1 divided by 2. So you need to plug all of this into function f. So go to function f and start rewriting it. That's 2 times x, but take x out, plug all of this in. X minus 1 divided by 2, and then don't forget the plus 1. Well, 2 and 2 cancel. I'm just left with x minus 1 and plus 1. They cancel. I'm just left with x. That looks good. Let's see if the other ones work too. Now we have to find g of f of x, right? So x goes into f first, but that already happened. When I plug x into f, I get this. So that is f of x. So f of x is 2x plus 1. So I have to find g of 2x plus 1. I got to plug all of this into function g. So go to g and start rewriting. Take x out, put all of this in. 2x plus 1, don't forget minus 1, and then divide it all by 2. Okay, so on top, plus 1 and minus 1 cancel. I'm left with 2x divided by 2. The 2's cancel, and I'm just left with x. So they cancel each other out. So that means since all of his operations canceled with his, and all of his operations canceled with those ones, you can say, yes, these are inverse functions. Okay, so this can be a little annoying, I know, because I'm sure nobody liked the composition of functions, but that's the way that you are supposed to verify if two functions are really inverses of each other. This is how you can show that their operations will undo one another, okay? All right, so I'm gonna give you a short homework on quizzes. So look for that on your Google Classroom. There should be a link for it. All right, good luck. And please, as always, text me if you have any questions. Good luck.